Okay, so carrying on from ions and identifying the appropriate charge on a particular ion, um, atoms can actually react together, if we have the right components, into what is called an ionic compound. So let me try to feed this in here a little bit. Right, an ionic, that's not spelled right, ionic compound is made from a cation or cations and an anion or anions. And we can think of ionic compounds, particularly when they're just between elements, as forming through the transfer of electrons. So as an example, right, we talked about lithium. A neutral lithium has 3 electrons, but it would gain stability if it could transfer one of those electrons. That'll get it to that configuration like helium that is more stable. We also said a fluorine, right, fluorine over on the right side of the periodic table, that's going to tend to want to gain 1 electron, and by gaining 1 electron it will also gain stability. So when lithium and fluorine, if we had a lithium atom and a fluorine atom, and we could put them together so that they came in contact with each other, what would happen is lithium would give an electron to the fluorine atom, right? And that would benefit both of them. They would both become more stable. Lithium would become a cation, lost an electron. Now there's 1 more positive charge from the 3 protons in the nucleus than from the 2 electrons in the outer shell. Fluorine now has become an anion. It's gained 1 electron. It's now got 1 more electron than proton, right? And now there's an attraction here between negatively charged species and positively charged species. So instead of writing these as separate, cation and anion, what we would usually do is write this as an ionic compound. So LiF, just lithium and fluorine. And this is always cation first, anion second, right? Or if it's just elements, it would be metal first, non-metal second. And in terms of the name, the anion, instead of having the name of the element, fluorine, which ends in INE, we change that ending to IDE. So the name of this compound would be lithium fluoride. Okay? Similar to sodium chloride, which you may be familiar with. That's NaCl, 1 sodium atom, 1 chlorine atom. They connect together, the sodium becomes a cation, the chlorine becomes an anion, right? And then we change the name of the ending. So it's not sodium chlorine, it's sodium chloride. Now, this is a pretty straightforward example because the charges are the same, right? What we need to factor in is the fact that not all the charges are the same. So what I'm going to try to do here is go through some examples, kind of show you how we can identify the name of a compound from its formula, or identify the formula of a compound from its name, taking into account what we know about the periodic table and charges. And I just want to make very clear, the only way to really get good at this is to practice. We're going to practice in lab. If this is a semester where this is a hybrid and you're going to be coming in for lab, we'll get to do some practice exercises. If that's not the case, there are plenty of practice exercises posted on the Moodle site. Make sure you practice. You really just have to kind of drill this into your head how this works. Okay, lithium and fluorine are in positions in the periodic table where they each have a charge of 1, +1, -1. Things will be a little bit different if we combine magnesium and fluorine together. So looking at where magnesium is in the periodic table, it is in a position where it is going to tend to lose 2 electrons to become magnesium 2+, right? But we know that fluorine is going to want to become minus. So if magnesium needs to become 2+, and fluorine needs to become minus, if we just combine 1 magnesium and 1 fluorine, we will not get a 0 net charge. The correct formula for any ionic compound should always have a 0 net charge, right? But we'd still have 1 extra positive charge if we just had 1 magnesium and 1 fluorine. What we need to do is balance the total positive charge with the total negative charge that comes from the anions here. So what we need is a second fluorine. So magnesium and fluorine combine together so that there's 1 magnesium and 2 of the fluoride anions. So the correct formula, based on the charges the atoms are likely to have in a compound, is MgF2. Right? Now the name is still just magnesium fluoride. Right? And a lot of times people are tempted to put in something to describe that too. Right? That is dependent on what type of compound you're talking about. If the compound is made of a metal and a nonmetal, right? Metals and nonmetals, it's an ionic compound. You don't put anything like a dye in there to describe the two. You just say magnesium fluoride. The ratio of the components is a function of the charges. So based on the charges we know those atoms are going to have when they become ions, we know that the formula has to be MgF2 without putting any other prefix in there to describe the numbers. Those prefixes will come into play for a different type of compound. Right? We can see something similar at work if, say, we take oxygen. So let's go back to lithium, which we know is going to want to be +1. Oxygen, as a nonmetal, is going to want to be 2-. It doesn't work if we just have one of each. Right? The ratio of components that's going to work is the one that's going to get us to a 0 net charge on the compound that we form. That means we're going to need 2 lithiums to get to a total charge of +2 to balance out the total charge of -2 that comes with 1 oxygen. So when we combine lithium and oxygen, the 2 will go along with the lithium. It would be Li2O in the formula. Right? But again, the name is just the name of the metal or cation, followed by the name of the anion, but with I to E at the end. So this would be lithium oxide. Now, if both the cation and the anion have a charge of 2, then we're back to just needing one of each. So if we take magnesium and oxygen, right, +2 and -2, combine those together, we're at 0. So just one of each would be appropriate, and that would be magnesium oxide. Okay. Now, certainly our nonmetals get into -3. We'll see there's some +3s, +4s, +5s we can get in the middle of the periodic table in the transition elements. So let me do just one more example. Say we go to calcium, right? Calcium's right underneath magnesium, so it's also going to want to be 2+. But say I'm combining calcium with nitrogen. Nitrogen is my nonmetal that's going to become an anion. +2 and -3. Well, the first place I'm going to be able to balance my charges here is the least common multiple of 2 and 3, which is 6. So what that means is when I combine these together, I need enough calciums to get to a charge of +6. That would be 3 calciums. And I need enough nitrogens to get to a charge of -6. That would be 2 nitrogens. So the only formula that works for calcium and nitrogen is Ca3N2. That's how we balance the positive and negative charges, or you can think of it as balancing the electrons lost by the calcium gained by the nitrogen atoms. Right? And then this would have the name calcium nitride. Right? Again, we're changing nitrogen, we're dropping the end of the element and replacing it with IDE. Okay? So if we're in the first 2 columns here, and in the nonmetals where we know what the charges are, right, it's a matter of ratioing them to get the right ratio to get to a 0 net charge. When we get into the middle, this is where the transition metals are. Things are going to get a little more complicated because we don't necessarily know what the charge of the transition metal is. So we'll come back to that and we'll cover that in the next video.